banked turns. Okay. Take a look at the diagram. As the car goes around the circle, notice that the center of the circle here is at a position that is straight horizontally from the car. If we're going in a circle, that circle defines a plane, right? A plane geometrically is like a flat surface. And all the points of this circle are coplanar. And the center of the circle is a point on that plane in the center of the circle. But it's directly horizontally from the car. It's not at the center of the track on the ground. It's not going to be like down here on the ground at the center of the track. So when we draw like a free body diagram for this kind of thing, centripetal is straight sideways. We are not using a tilted system where centripetal is down. This is not the center of the circle down here. Because if you made that the center of the circle would be this direction, and the other side of the circle would be down here. You know, it'd be like underground. We are going in a flat horizontal circle, and so the center of that circle is directly horizontally from the car. That means our coordinate system is not going to be tilted. It's going to be a vertical and centripetal system, not this tilted thing that we've used before. This is a very common point for people to make an error right at the beginning of this kind of problem. If there's no friction, there is exactly one speed that's going to work for you to go around this circle without either slipping up the bank or sliding down the bank. If you go too slow around a banked curve, if you're going too slow, your car's going to have a tendency to just slide down. If you're going too fast, your car's just going to have a tendency to slide up. This is similar to the conical pendulum or the flying pig lab. The slower the pig flies, the smaller the circle it's going to make. The faster it is, the bigger it's going to be. Same thing here. The slower the car goes, the farther down the bank turn it's going to go. And as the car comes down the bank turn, it's decreasing the radius of the circle. The faster the car goes, it's going to want to slide up, and as it slides up, it's going to increase the radius. So if you want to navigate this with only one constant radius, you have to be going at the exact right speed so that you don't slide up or down. So what we can say about that is there's one speed that works to get around the corner for any given radius and angle of bank. If you change either of those things, the radius of the circle or the angle of the bank, the ideal speed will change. The normal force is not going to be equal to gravity. When you look at the free body diagram here, the normal force is actually this line. This is a component, this is a component. Gravity is straight down. The normal force is at an angle. It's the y component of the normal force that's equal to gravity, and the centripetal component of the normal force is what provides us with our centripetal acceleration. Fn sine theta for the centripetal part, Fn cosine theta for the vertical part. This should make sense because what happens if theta goes to 0? How much of the normal force is going to be vertical if theta is 0? On flat ground, all of the normal force is vertical. And what do you get when you put in cosine of 0? You get 100% of the normal force. At 90 degrees, so imagine the wall, the car's driving on a wall. At 90 degrees, all of the normal force is horizontal. And that's what you get when you plug in sine of 90, 100%. So to find that ideal speed, we can't just set normal force and gravity equal. It's the y component of the normal force that equals mg. And overall, the normal force will be more than mg. So, 'cause In the y direction, we know we have 0 acceleration because we're not moving up or down here. So we get Fn equals mg over cosine theta. In the centripetal direction, our acceleration is v squared over r, and all of the centripetal acceleration is provided by our normal force. That's Fn sine theta. I take what I know from the vertical direction, plug it in, and then I solve for velocity, and I get the square root of gr tan theta. That is the ideal speed to go around a banked turn with radius r, banked at an angle theta without slipping up or sliding down, no friction. Now, if the car goes at the ideal speed, no friction is needed. So the first thing to do in any problem that involves a banked turn is figure out what the ideal speed would be without friction. If the car happens to be going that speed, great. No friction is even needed. Even if they say there's a coefficient of friction, it's not going to be needed, because remember, static friction can adjust itself, and in this case, at the ideal speed, it's not needed at all. But if the car goes faster than the ideal speed, the car wants to slide up the hill if it goes too fast, right? If you're going around a corner and you go too fast, which way is the car going to slide? Away from the center of the corner. It's not going to make you go around the corner even faster or even tighter. If you skid out of a corner, you skid out of the corner. So if the car goes faster, the car is going to want to slide up. And if the car wants to slide up the bank, friction is going to have to point down the bank. Conversely, if the car is going slower than this ideal speed, then the car would want to slide down and friction would need to point up to keep it up. So like I said, anytime you got a banked turn problem, figure out the ideal speed first, and then if your car is going faster than that or slower than that, you can figure out the direction of friction. Sometimes though, they'll tell you a speed and you'll need to figure out the ideal speed and then see if you're going faster. Or maybe they'll tell you a speed and a radius and they'll ask you to find an angle that works for it. There's lots of different ways to phrase the questions, but these relationships will always hold. So with friction, if you're going faster, remember friction, if you're going faster, you want to slide up the bank, so friction has to point down. So I took this free body diagram and I broke it down into the y direction. In the y direction, we have friction up. Notice that this, we have the normal force up. Notice that the friction points left and down. Now left is the centripetal direction. So we have a component of the normal force here. And we have friction here in the centripetal direction. And both friction and the normal force are pointing towards the left, which would be towards the center, because this free body diagram represents this car right here, but with friction. This is like a free body diagram without friction. So part of friction points towards the center, part of the normal force points towards the center, and you would add both of those up and set it equal to mv squared over r. In the y direction, we have a component of the normal force pointing up, but friction, since it's pointing down the ramp, part of friction actually points down along with gravity. If we are going too slow, notice how friction flips. If you're going too slow, you want to slide down the ramp. Friction needs to point up the ramp. And now, since friction is pointing up, we'll have friction in the y direction going up, as opposed to this one where friction in the y direction went down. Also, friction now is pointing towards the right, but the center of our turn is to the left. So friction then becomes a negative force in the centripetal direction, and Fn sine theta is the positive force. So all I did here was show you the free body diagrams, and based on those, you should be able to figure out, your sigma F equals ma and deal with whatever problems you might have. The note here is just about how static friction slips direction or flips direction when you go from too fast to too slow, and the components are going to flip, right? So this blue line, which was down and left, is now up and right. And static friction, which used to go down, now points up. And when it used to go to the left, it now goes to the right. So all the friction components flip when you go from too fast to too slow. We've got a couple more example problems that we'll do here. First, we've got an amusement ride where this compartment drops and then it goes through a corner and onto the track at the bottom. So the track is frictionless as it falls, and we want to draw a free body diagram at point C, which is some angle through the curve, and we want to find the magnitude of the centripetal force there. And then we're going to repeat the situation. Friction is going to start instantaneously at point C. We'll want to draw another free body diagram and compare how the centripetal forces are in each of those situations. So in A and B, A is our free body diagram with no friction. We have a centripetal force, which is perpendicular to the surface, so that's towards the center. And then we have gravity, which is straight down. Now, this gravity vector, which is straight down, we can break that up into a tangential component and a centripetal component. And you can see the coordinate system I'm using here. Centripetal is towards the center, right? Towards the center. And then I said, this kind of upwards direction was positive for tangential, but there's no reason why you couldn't take this tangential component and flip it and have it be downwards. Whatever works. The tangential component's not really important to this problem, so it doesn't matter. But it's the sum of these two forces here that provide us our centripetal force. That centripetal force is mv squared over r, and that is the magnitude, the net centripetal force. Net just means the sum of all of them, right? Like the net force is the sum of the forces. So the net centripetal force is the sum of them, which is mv squared over r. If we wanted to find the actual normal force here, then we would have Fn, which is in the positive centripetal direction because it's pointing towards the center, minus the force of gravity in the centripetal direction, which is actually opposite, and that's Fg sine theta. Remember, theta is measured from vertical here. So if we were at point B, how much of gravity points towards the center at point B? None. And point B is when theta equals 0. And if you put a 0 in here, what does this term become? None. So we just rearrange this, solve for Fn. That's just a little bonus question I thought I'd throw in there. For part C, when we deal with friction at point C, which way does friction point? Opposite the direction of motion. The direction of motion is tangential, so friction points in the opposite direction of our tangential velocity. And the centripetal forces are going to be the same. Friction does not affect the centripetal forces, right? Now, if you had already encountered friction for a while, friction will slow you down. When friction slows you down, you're going to have less centripetal acceleration. And if you have less centripetal acceleration, that would reduce the normal force. So this result here for part D is really only true if it's at the first instant you encounter friction. If it was some time later, the normal force would be different, but if it was sometime later, the other components would be a little different as well, because you would have changed the angle theta. So complicated situation, but there's a little glimpse at it. In this next question here, we've got a nonlinear spring. That just means it does not obey Hooke's law in the standard sense. And this nonlinear spring has an equation of F equals AX squared. That's just like F equals KX, but instead of KX, it's X squared. So it's proportional to the displacement squared. That means if you compress it twice as much, it's actually going to push 4 times harder on you. You could accomplish this in real life by like taking a spring and changing the amount of coils per unit length. You could change the radius of the coils maybe. You could actually change the thickness of the wire. The thicker the wire, the stiffer it's going to be. And the thinner side would compress easier. The thicker side is going to be more difficult to compress. So there's a few different ways. You could also change the material that it's made out of. If you had the ability to like change the material that a wire was made out of, but keep the thickness of the wire the same, and then you could wind that into a spring where the material properties changed over the length of it, you could change the amount of force and how that varies as you compress the spring. So when you're asked to create a linear graph whose slope can be used to do something, it's very common in these kind of problems. That means you're linearizing the graph. You're linearizing your equation to make it a linear graph, right? Linearized linear graph. Y equals mx plus b, typical linear equation. And what we want here is to get that f equals ax, and I realize I wrote a lowercase a. There we go, capital A. F equals ax squared. We want to get that to match up with y equals mx plus b, where the letter a is going to be related to the slope where m is. There is 2 different ways of doing that for this kind of problem. Option number 1, I can take y equals mx plus b, and if I write our equation, f equals ax squared below it, I can tack on a 0. Adding 0 doesn't change anything, so our y-intercept is 0. Where we have the vertical axis, we'd have force. The horizontal axis would be x squared, and then a and our slope are in the same place. The other option here would be to take the square root of both sides of this. Now, when I take the square root of both sides, I'm going to get the square root of f, the square root of a, and the square root of x squared is just going to be x. And here, notice that the slope is the square root of a. Both of these options will work. They're both correct. You could do either one. The first one you'll probably find easier because in the first one, you will get your slope and it will be your answer. In the second one, you're going to have to find your slope, and then what are you going to have to do to it? You're going to have to square it. So there's like one more step in the second one. So I used option 1, and this was the graph that I used. You're going to want to fill in your data chart here. Now, I chose to fill this in with numbers that were times 10 to the negative third, just so I didn't have to deal with as many decimal places. If you want to write them down as decimals, feel free. This axis here, the horizontal axis, was also times 10 to the negative third. So if you did this with decimals, this would be 0.07, 0.04, 0.01. My y-axis was force. You're going to want to plot the data points, draw in a line of best fit, of course using your straight edge. Pick 2 points on the line that are not data points. I found using 0, 0 was easy, right? I mean, if you don't compress the spring, guess what? It doesn't push at all. So if you can use 0, 0, great. Don't force your line to go through 0, 0. But if it makes sense that your line goes through 0, 0, you can put it through 0, 0, and you can use that, and it just makes finding your slope that much easier. A is our slope. Show the work, and I got something around 1,700 newtons per meter squared. You should get something in the ballpark of that. We've got one more example we're going to look at on the next page. We've got a 5 kilogram block sliding on a smooth frictionless surface. I've given you the speed, and it encounters a rough section and slides to a stop over a distance of 3 meters. For reference, 13.73 meters per second is going to be somewhere between 25, maybe 30 miles an hour, so it's fairly quick. And if you're stopping from 30 miles an hour over the course of 3 meters, which is like 9, 10 feet, 10 feet, 30 miles an hour, you know, that's along the lines of like maybe a car crash here. So this is a pretty severe stop that we're coming to. And if our block was sliding towards the right, friction is going to be to the left. We got a normal force. We got gravity down. Here's my coordinate system. Right's positive, up's positive. In the y direction, we know the sum of the forces in the y direction is 0, which means our normal force and gravity have to be equal. In the x direction, we know sigma f equals ma. You can, on your own, show that when you plug this in and work it out, you get a value for mu that is minus a over g. What you will then also have to do is use kinematics to find the acceleration in another form. Take what you get from the acceleration here, plug it in up here, and then you will get a value for mu, which I found to be 3.14. Hopefully I didn't make a mistake with my calculations. You should actually be pushing the buttons on your calculator to double check this sort of thing. There's no units with mu, so I didn't forget to include units with a numerical answer. After we've got that in part B of the problem, you're going to find the acceleration using part A. Now we know what mu is. Now you go back up here, rearrange that equation, find the acceleration, plug in mu, plug in g, and then use kinematics with the given information, and you should find that it takes about 0.43 seconds for this thing to stop over the course of those 3 meters. All right, so you're filling in this part on your own. You're filling in this part on your own. You did that on your own. In parts C, D, and E, you're going to write a differential equation based on Newton's second law. Find the velocity as a function of time, and then find how far the block slides before it stops. This time we are dealing with drag, whose magnitude is kV, but there is no more friction. So, drag to the left, normal force up, gravity down, no force to the right, sigma F equals ma, that's negative friction, and we substitute A as dV dt. That's our, right there is our differential equation. I actually went one step farther than that, and I separated the variables. You would be totally fine ending right here. You don't need to separate the variables to get a differential equation. So maybe this would be better in pink, since it's really the beginning of step D, where we're going to solve to find velocity as a function of time. Separate your variables. V, all I needed to do was divide V over here, multiply by dt, divide by m. So when I got dv over v, I'm going to integrate that and get an ln function. On the left side, the integral of dt is just t. And at time 0, my speed was v0. At some later time t, I'm going to have velocity v. So I plug those in, I evaluate. Remember, when you evaluate this, you're going to get ln of v minus ln of v0. Use your property logarithms. That becomes a division. Put each side as a power with a base of e. A base of e to a power of ln cancels. And we get this. Does this make sense? The function we have on the left side is an exponential decay starting at v0 and asymptotically approaching 0. So that makes sense. For part E, we want to find the distance that we slide. Now, our velocity is the time rate of change of position. We will again separate our variables. So I'm going to multiply this dt over to the right so I get my t's and my dt's on the same side. This dx is just going to stay here on the left. As I integrate, I want to know how far this thing slides before it stops. That means all the way out, however long it takes. Let's go all the way to infinity for time. And we're going to start at position 0. We're going to stop when we get to some final resting spot. When we integrate this, we're going to get negative m over k, which is the reciprocal of what we have up top, times v naught e to the same stuff. Now imagine taking the derivative of this. The derivative of this would be all of this times the derivative of what's up top, which would be negative k over m. That negative k over m would cancel with the negative m over k, and we'd be right back here. So that works out. Then when we evaluate, e to the negative infinity is 0. E to the 0 becomes 1, and we have this stuff. But remember, it's upper limit minus lower limit. So we're minusing the lower limit, but the lower limit was also came out to be a negative. Those two negatives cancel, and we slide a distance of m v naught over k before we stop. And the last note I said here was that that was my mistake. I should have actually, in the setup for the problem, in the text up here, I should have given, instead of just the letter k, I should have actually given a number. And then we could have had a numeric answer for how far it slides. But you can see how far it's going to slide here. As the value of k becomes less, as k gets smaller, it ends up sliding farther. As k gets bigger, it ends up coming to a rest sooner. What kind of things does k depend on? K would depend on like the shape of the object. K might depend on the density of the air. The temperature or the humidity that day is going to affect like how thick the air is and how much it stops you. So those kind of things would determine the value for k. The specific shape of your object, its cross-sectional area, and the properties of the atmosphere on that given day. But there's an example of that drag, and that wraps up this section of the notebook. We're done with Unit 2 now. Thanks for hanging in there, and we'll catch you next time.